Great. I think we're all set to go. Welcome back, everyone, to this month's webinar. Hopefully a lot of you are coming back from last month's. This month we'll be covering ground bond and ground continuity testing. So before we begin, let me introduce you to our team again. I am your presenter, Anthony Arroyo, Applications Engineer here with Associated Research. Our panelist will be Bashan Patel, another Applications Engineer, and our organizer extraordinaire is Allison Oba. If you have any questions or are having any issues hearing me or seeing our presentation, feel free to use our chat feature to contact Allison, and she'll make sure you're squared away. This webinar will be recorded and will be available for anyone who would like a copy of it. All our webinars are recorded and available to you through us directly, or feel free to visit our YouTube page, AR Hypot. So we have Allison's email, allison.oba@arisafety.com if you would like a copy of this presentation or any info or any of the information you'll receive through this information. We'll gladly send that out to you. So quickly, let's recap our last webinar. Hypot Testing 102 is pretty much our most popular webinar. Obviously, hypot testing is the most prevalent test in most standards. We covered AC versus DC, what 500 VA means, some of the features, and how to set your parameters, high and low limits. So again, if you missed that one or you want to go back and check out Hypot Testing 101, feel free to contact Allison. Now today, we're going to be covering ground bond and ground continuity testing. It's pretty much behind hypot testing. It's the second most common and prevalent test in standardized testing, product safety testing. So we'll go over what is ground, grounding of electrical products, class 1 versus class 2, which I'm sure most of you are very familiar with. We'll get specifically into ground bond, what it is, some examples, then we'll cover ground continuity, so the differences between those two, and then we'll see some videos explaining the differences, how to set up, and we'll delve into some standards, actually specific standards and the verbiage that they use, because I know in the industry we can use a lot of different terms for the same test. So first, let's get started with what is ground. Ground, or earth, it can have numerous functions and meanings. It can be a reference point. If it's tied to neutral, it can be the low side of your voltage or your potential difference. It can be the second line of defense against electrical shock. So it will be what picks up all that leakage current or any fault current that may occur. And it's a common return path for electrical current. But all in all, I think the purpose of ground is to reduce the risk of electrical shock. It doesn't eliminate it, but it does reduce it. Depending on how long that path is, you're gaining more resistance in your ground. So eventually there's going to be a limit of how much current it can carry, and that current can look for a different path. So it will never, 100% eliminate the risk, but it's a great way to reduce it. Here, let's take a look at modern power distributions. So just in your home, we can see here we have our power or current coming in through our power lines, and you can picture this resistor as all the products connected in your home. Normal functioning, it will go through your system, back out through neutral, back to the source or the power lines. Now, if some sort of fault condition were to occur, this is where your grounding comes into play, or your ground circuit. That fault current will be caught by that ground and be delivered back to your source. That way it's not floating on top of any chassis or metal handles, anything exposed to yourself or users. So it mitigates the chance for shock. There's obviously different functions of ground. We have a service ground, which is kind of what we were referring to in the last slide, or what probably everyone watching this webinar is here for is your equipment ground. You know, the ground that is inside your products or DUT and is meant to catch any fault current. So we refer to that as ground or earth. System or service ground, that's designed to protect machines, that's designed to not overload your equipment. So if you buy a generator, you know, you're protecting your equipment. You know, you spent $1,000 on a generator, you don't want it to blow. So that's what the service ground is for. Now the equipment ground, that's designed to protect the operator or the user, the consumer, from electrical shock hazards. We'll obviously be concentrating on the equipment ground today. Class 1 versus Class 2. Again, most people watching this webinar are here because they have a Class 1 product. It terminates in 3 prongs, line, neutral, and ground. The ground prong, somewhere along your product, is connected to the chassis. That way there's a path for that fault current to travel back to the source or back to ground. Where Class 2 products obviously use double insulation. So we're going to be focusing on Class 1 products. They provide electrical protection by employing basic insulation, and its second way of protecting you is having a grounded chassis. So it's a double layer of insulation. So what is a good ground? There's ground standards called out in UL standards and, you know, NRTL type testing, and then there's also NEC codes that state it's to protect people and property from electrical hazards. You know, NEC 250-45 states any exposed non-current carrying metal parts of a cord. So meaning it's not designed to carry any current. It's not there as a functional use. You know, we won't be purposely passing any current through that path. And a plug connected equipment which may become energized shall be grounded. So pretty much if there is an area of your product that may carry fault current, we want to make sure it's grounded so that current finds a path back to ground. So NEC 250, expanding on that -51, it's permanent and continuous. So continuous meaning, you know, the path is a full loop. The capacity to conduct fault current, so obviously we want it to be conductive, and low impedance. The lower the impedance, the better. The more current it can carry, and the less chance of it finding a different path, most likely the user or the operator. The NFPA, National Fire Protection Agency, stipulates the NEC, which is adopted in all 50 U.S. states. The NEC gives requirements for grounding products and installations, and the NEC also defines a good ground, as we just explained. So the ground bond and ground continuity test. Before we get into how we test and where these parameters come from or where these limits come from, we just want to make sure we understand the purpose and their definition. So the purpose of ground bond and ground continuity test are designed to check the ground connection on a product or system. You know, how you ensure you have a proper ground. The method is to apply a current depending on what we're talking about. Ground bond, you're applying a large amount of current, where ground continuity, it's a very small amount of current that can actually range from 1 milliamp to 100 milliamps. Some of our new testers go up to 1 amp. Apply a current to the ground point of a product or system. You measure the potential drop across the ground circuit and calculate the circuit's resistance. So in the standards they're called out, you know, you need a certain amount of voltage. And the voltage drop across the resistance of your ground, this is how you identify the amount of current going through and the allotted resistance you're allowed to have per the standard. Testing. Ground bond are generally type tests. Recent trends have shown that a lot more people are using it in production. We'll expand into that a little bit later. Ground continuity are generally production tests. So these two types of tests are used to prove and verify that there is a low impedance path to the ground for electrical products and system. This ensures proper grounding. So here's our ground bond test. There's a couple different ways to apply this. So this is our dedicated ground bond tester. We call it the high amp. Here's our 3130 setup. You can see we have our high current connected to the ground pin of our plug, and the return to an exposed chassis point or an accessible chassis point. Now, an issue you might come across with this setup is there's also resistance in these leads. You know, this high current lead and the return lead. So it's not fair for you to test your product and the resistance of our test leads be counted in that value as well. So in this situation, we would use our offset feature. You know, we offset our leads, we disconnect them, hook them up together, and run your offset, and we'll find the value of the resistance in those leads. That way, that'll be subtracted from your final results. Now, you have this other method, which are 31, 40, 45, and 60 have 4-wire measurements or Kelvin measurements, where your output comes from this current port through the product back into this return port. But we have these sense terminals that are actually connected right at your connecting points. So the resistance from your leads are nowhere in your result measurement. So those are two methods. Obviously we have other instruments, 6-in-1, 4-in-1, that also have this Kelvin measurement and offset feature. So it's important if you're close to that borderline, that high limit of your standards resistance, so 100 milliohms or 200 milliohms, you want to make sure you're utilizing offset features or a 4-wire Kelvin measurement. So here's your ground bond test internally. Here's our current source. We are connecting that current source. We can assume this is an adapter box, or you can visualize this as your connection. Your connector to your ground pin. That current will be going through your ground wire. This is the resistance in your ground wire. That current will return to the source, but the measurement is being made at the DUT connection, therefore mitigating any resistance from our leads. In an ideal situation, that current will flow through. This resistance will be low enough where it will not set off your high limit failures and returns back to the ground path. Now, in a fail condition, this resistance is way too high. It will set off that high limit failure, and now you know, hey, my ground path has way too much resistance, meaning, so why do we want it to not have a lot of resistance? Because if you were to start selling these and a fault condition were to occur, and now a lot of current is leaking to your chassis, well, there's way too much resistance on your ground path, so it's going to find another path, usually staying on your chassis waiting for an operator or consumer to touch it. So that's the point of having those limits set and those standards, which we'll get into a little bit more. We'll actually look at a 60601-1 standard where it specifically states how to test your ground circuit. So here is a portion of our standards reference guide. We've actually made a standards reference guide that kind of gives you quick hits on what the requirements are, you know, what frequency, what parameters you should be looking for. If you don't have a copy of this, feel free to reach out to Allison. She can email you or send you the link on our website where you can find this. So this specifically is IEC/UL 60601-1, which is for medical devices. 8.6.4 impedance and current carrying capability. So the requirements are 25 amps or 1.5% the highest rated current, whichever is greater, plus or minus 10%, pass through the protective earthing circuit. Like, this is the first time I've said protective earthing circuit. There's so many different terms for your earth, your ground, or your protective earthing circuit, which makes it real hard to understand standards sometimes. The pass criteria for this would be impedance protective earthing circuit on the DUT needs to be less than or equal to 100 milliohms. For DUTs with non-detachable supply cords, impedance for the DUT, you're allowed a little bit more, less than or equal to 200 milliohms. So we've kind of done the work for you. We've created this standards guide, and instead of having to read through all that crazy verbiage in the standard, you can kind of have a quick reference. Like I said, if you need it, feel free to reach out to Allison. But that kind of brings up a question that I'm interested in, as well as I'm sure you're curious how your peers feel about reading and translating the standard. So Allison's going to open up this poll question of how confident are you in your translation and implementation of your standard. The standard has a lot of different ways to call out certain tests, and I think a lot of it falls on us as well. We happen to call certain tests different than the standard does, so it can get confusing. So I'm curious, on your side of things, when you read a standard, do you feel confident in your understanding what it's saying, what applies to your specific product? And if you do feel confident, is that because you've hired a compliance engineer and it's their job to make sure they understand how to test? Did you develop experience through dealing with UL or TUV, any NRTL where they've kind of given you guidance? Now, the issue with that is, sure, you've gained experience, but maybe you had to fail once or twice while testing with them. So you gained experience, but now you have to open up a new project with them and pay twice. Or are you in that state where you're doing it for the first time and you're kind of learning as you go? You're kind of hoping your product's going to test since you've sent that to UL or TUV or ETL, any NRTL. There's a lot of cost that comes with that, because if you haven't been doing this testing on your own and you're sending it to an NRTL, you're going to get great feedback, of course, but you might fail, and they're going to charge you again to send it through. So it's great if you have that experience already. Or the other option is, I'm positive that I'm doing it wrong and I need training or consultation. So Allison can give us those results.
All right, everyone, thank you so much for voting. I'm going to go ahead and close the poll. So your responses to how confident are you in the translation and implementation of your standard: 36% were very confident, 36% were only confident, and 29% are not confident. And it's kind of a good thing. 0% of people are not confident. So, a lot of people don't really necessarily feel like they need additional training right now.
That's good. That's good. So 29% are kind of learning as you go, 36 and 36 are confident. So that's good. So what I want to do is kind of look specifically at a standard. Obviously there's a lot of copyright issues that come with sending out standards, so we don't do that. But showing you a snippet of a common standard that many people probably that are attending our webinar test to. So this is actually from Medical Devices 60601. This is actual standard verbiage, protective earthing, functional earthing, and potential equalization. Accessible parts of Class 1 equipment. Accessible parts, what's that mean? Anything I can touch, anything your user can touch. Separated by from live parts by basic insulation, so that makes sense, shall be connected by sufficiently low impedance to the protective earth terminal. So this is what we're talking about, having some sort of stud on your chassis where all those accessible parts are somehow connected back to your protective earth terminal so that any fault current can be sent through back to ground. So we understand that's pretty easy to understand, but still some of that some of those terms, I haven't used. If we look down to, so now we know that our accessible parts need to be grounded. How do we test for that? For equipment without a power supply cord, the impedance between the protective earth terminal and any accessible metal part, which is protectively earthed, shall not exceed 0.1 ohm or 100 milliohms. We have, again, you need to be able to identify where does my product fit in the standard for equipment with appliance inlet, for equipment with non-detachable power supply cords. And a lot of these standards refer to different sections and other standards. So it can be really complicated, and sometimes, it can be good to have a little bit of training or consultations in identifying the proper way to test your product. So most people, I think, fall into the other categories, not quite the non-detachable power supply cord. So most of you are probably setting your high limit at 100 milliohms, where those with non-detachable supply cords are setting it at 200 milliohms. And so compliance is checked by the following test. It's not giving it, it's not, ground bond isn't stated anywhere in this section, so it's something you kind of have to become familiar with. A current of 25 amps, or 1.5 times the rated current of the equipment, whichever is greater. From a current source with a frequency of 50 hertz or 60 hertz, with a no load voltage not exceeding 6 volts, is passed for 5 seconds to 10 seconds through the protective earth terminal or the protective earth contact in the appliance inlet. So this is exactly what this is our ground bond test. Delivering a high amount of current through your ground circuit for 5 to 10 seconds and making sure that your resistance does not exceed our high limit. Now, here's another part of the standard. This annex does not come, right after the part I just read. I copied a different part. So this is for manufacturing and production tests. So here you see you have to do a high-pot test during manufacturing, you have to do a ground continuity test, and a single suspension test. So the ground continuity test, each appliance that has provisions for grounding by fixed wiring means or has a power supply cord having a grounding conductor shall be tested as a routine production line test, meaning you need to confirm that your ground test has continuity. So nowhere here is it stating you need to perform a ground bond test during production or manufacturing. But as I was kind of hinting to earlier, we're noticing that this is quickly becoming a trend, because running a ground bond test is, you're doing both, you're kind of killing two birds with one stone. It's the same as running a continuity test, If you're passing your ground bond test, then you have peace of mind that there's continuity in ground. So while it isn't called out, it's
Hi, Tony. I'm sorry to interrupt you, but we might have lost your audio.
during manufacturing. So again, thank you for the feedback on the poll question. It's great that most people feel semi-confident on what they're doing or just translating standards, because you come out with a new product, it's a completely new standard you'll be testing to.
Hey Tony, sorry to
So
disturb you.
here's some more type
Can
testing
you hear me, Tony?
tests for, this is the luminaires, CSA or UL 1598 slash, in Canada it'll be C22.2. Now the requirement here is to test 30 amps through your ground, and no load voltage should be less than 12 volts. And your test time is 60 to 120 seconds. So that's a lot of stress on your ground circuit, 30 amps for 120 seconds. And then your impedance cannot pass 100 milliohms. So we're just going to kind of run through a couple different ones just so you can see the type of parameters or what you should be using. Here is UL 60355. We have 25 amps and again 100 milliohms. Your ground circuit should not have more resistance or impedance than 100 milliohms. So let's jump into the ground continuity test. It's a DC low current test to check circuit resistance. We don't, similar concept to ground bond testing, so we don't want that resistance to be too high. If it's too high, it's going to consider it an open, and you're going to fail continuity. Method, not all readings are displayed in ohmic value. Sometimes it can just be an indicator, a light or buzzer meters to check whether continuity exists. Some of our high pop machines do ground continuity and high pop, where once you make your connections, if the green light LED illuminates, then you're good to go and you've confirmed continuity. So the ground continuity testing is the same concept as ground bond testing. You're simply checking for a continuous path on a ground circuit. However, there are key differences between the two tests. You know, the ground continuity, we're not trying to stress your circuit. You know, if we see a certain amount of resistance, our instruments will change ranges and start outputting less current, because we want to make sure we're not trying to test the integrity of your ground circuit. We just want to make sure there's a continuous loop. So I'm sorry, I should be in presentation mode. So let's look at what the standards say about continuity tests. A continuity test to be run on protective earth circuit, no current value specified, so it depends on what your manufacturer has as their specs. When it comes to our, so continuity is usually part of HiPot. This is why we have our HiPot tester here, but continuity on our instruments can range from 1 milliamp to 10 milliamps to 100 milliamps, depending on the impedance seen on your ground circuit. That's associated with your HiPot test, so a lot of, when you see continuity, you will see, you know, your HiPot test voltages also on the same area. So for UL 60355, which we were just discussing, there's a routine ground bond test current at 10 amps, and impedance of earthing conductor for cord connected equipment should be less than 200 milliohms, while most of the other applications will be less than 100 milliohms. So now that we've kind of had a brief overview on what the standards say about both, let's kind of compare and contrast both of them. Ground continuity verifies the existence of a ground connection, while ground bond verifies the integrity of a ground connection. The readings of ground continuity are generally given in ohms, while the readings are generally given in milliohms for ground bond, because the limits for those are usually 100 milliohms or 200 milliohms. So the ground continuity, it's a quick test to set up and easy to perform, usually done in manufacturer settings. Now, I think when manufacturing or in production, time is an issue. So a lot of our instruments provide ground continuity and high pot done at the same time. And we also have interconnect features where you can do ground bond and high pot at the same time. So if you feel like on your manufacturing floor you're trying to, because I know those are seconds, for each product you want to spend no less than a couple seconds on verifying and getting them shipped out. So if you feel like there's some opportunity there where you're looking for quicker turnover in manufacturing, we can kind of talk about our interconnect features or our ground bond, dual testing, ground bond and high pot testing. Getting back to the comparisons, usually used as an extra feature during the high pot test, where ground bond can be combined with a high pot test for a more complete safety testing system. And the ground bond test, it also provides more valuable safety information about the DUT. You can kind of identify a range. If I've just tested 10 products and I keep track of the milliohm readings of those products, you can kind of gauge what the general characteristic of your ground circuit is. And you can start decreasing those limits so that you kind of get uniformity in your ground circuit. Kind of helps maintain quality of your product and uniformity in general. So just to kind of drive home the idea between ground bond and ground continuity. If you were to have a wire like this is absolutely going to pass ground continuity. But depending on how much current you're delivering in your ground bond test and for how long, this will probably not pass ground bond. So this is a 64-strand wire with all but one strand. It should be all but one strand disconnected. So ground continuity you're going to pass because the instrument still reads a continuous path, while in ground bond that is going to burn up because the resistance of that one wire is just way too high to handle that current. The wider we make, or the gauge-wise, the wider we make our wires, the less resistance they'll have. It's like a highway. The more lanes, the wider that highway is, the less traffic we'll get. Whereas opposed to a one-lane highway, there's going to be a large amount of traffic or a large amount of resistance. So using Ohm's law, if I'm giving constant current, if my current value is the same, but now my resistance is higher, that's a large amount of voltage. And something like this one strand just can't handle that type of current. So I want to do a video demonstration here so we can kind of see what's happening during high pot test. Oops, sorry about that. So here we have an ordinary soldering tool. All right, we can see our connections. In the video here, a little later, we'll see where this leads to, but right now I'm connected to my ground pin, and my return is to an accessible part. Any part that a user may come into contact with. If we look at our test that we're about to perform, we're going to perform our continuity test first, and my limit for that will be 100 ohms, and then I'm going to perform a 40 amp ground bond test. So that's probably way more than most of you are testing with. That's actually the limit. That's our capability of our Omnia here. So our Omnia is our 6-in-1 tester, which can do continuity, ground bond, AC, DC, high pot, insulation resistance, and a lot of you are here for 60601-1. It does those leakage current testing with fault conditions. Going further down the video, I want to show our connections. Let me forgive the So when the test is running, there's no visible signs on the DUT, right? There's, whether you're doing a continuity test or you're running a ground bond test, you can't tell visually. But in certain seconds, like right now, we just went from continuity to ground bond. So now we're feeding 40 amps of current through this soldering iron, and I am getting 89 milliohms of resistance. So I'm getting pretty close to my high limit of 100 milliohms per the standard. So if I was this DUT's production, if I was the company that produced these soldering irons, I see my resistance is near 89. So what I would want to do to create uniformity within my products is I can set my high limit, keep it to 100, which is what the standard calls out to, and maybe make my low limit 80, because if I'm not hitting my low limit, that means that input wire that I have on this DUT is different from the one that I've been seeing on the previous tested DUTs. So either something's changed with my manufacturer, or there is some sort of defective quality to that wire. This is what I mean when you're creating uniformity within your product, where although all those different input wires might pass, they have different characteristics. So as a company, I would feel more comfortable knowing all my parts have similar characteristics and I can depend on them to perform a certain way. So I'll let this video go through. You can see I'm delivering 40 amps through this ground circuit, which is a large amount of current, and visually we're not really seeing anything. They both passed. Sorry, let me get back to the results screen here. So it stayed consistent at 89 milliohms, which is good. It's close to 100, but still passing. I mean, that's a very low impedance. And continuity-wise, 200 milliohms. Sorry, I was moving the decimal in my head to make sure, 200 milliohms. So that's all fun and good. We saw proper connections. We saw that there are no visible indications of what's going on when performing the test. So I have a separate video here to show you what's going on with that wire. So let me cut off my camera, because I know sometimes one of my cameras on these videos can get choppy, as what we just saw. So let me close this one and open this guy up. Let me open this with a different player, a little bit smoother for you guys, because this is the cool video, so I want to make sure. So here we have our same parameters, or same test, I'm sorry. I kind of turned off my limits because the limit would stop the output current. I want to show you worst case scenario, what could happen. So what I'm doing here is testing. Okay, so here's a great shot of our 4-wire Kelvin connection that I wanted to get to. Our high current is coming out of our red lead here, going through our DUT back to the return, while our sense plus, sense minus connections are making the measurements at our connections, so you don't have to worry about creating an offset. You don't have to worry about the internal impedance of your test system or the cables. You know, some people can use 10-foot cables, 20-foot cables, 5-foot cables, regardless. That creates extra resistance on your test. And if you're not offsetting that, you could be getting false failures. So we let this run. We saw our settings. We're going to run a continuity test. Now I'm testing just a wire that some manufacturers might use. It's technically a paper clip, but you know, envision, it's still a wire. Envision this as your ground continuity. If I'm running production and I'm just doing continuity, this passed. I'm good, and I'm shipping it out to my consumers. Now I'm running it for 10 seconds, it passed, and it's moving down the line. Now if you're running a ground bond test in production, let's see what happens here. So obviously the impedance on this paper clip could not handle the 40 amps we were delivering to, and this is how fires can start. You know, if that customer that Bashan was dealing with was not running ground bond in his production line, those products would have been shipped out and it would have created some dangerous situations. So let's go back to our presentation here. It's a pretty cool video. I think, so let's summarize ground bond versus ground continuity. What is ground? We've discussed what is ground. There's different terminologies that refer to ground as different terms, so it's important to kind of identify how it's called out in your standard and how it's called out in our instruments. You know, our instruments will say ground bond test. It won't say protective earth circuit. We identified class 1 versus class 2 products, compared and contrast ground bond versus ground continuity, and we showed some examples. So we have some time here. I know Bashan has been answering questions from our viewers. If there are any questions that he feels are relevant, he can chime in, or we can open up the chat to see if any questions have been asked that would be good for the entire audience to hear. While we're doing that, we want to let you know to join us for our next webinar, which is Wednesday, June 22nd. Again, 60601-1, Leakage Testing 101. You know, this is the first part of a two-part series where we'll talk about all those fault conditions, from open ground to open neutral, reverse polarity, what they mean, how our testers do that, and if you're properly testing with, if you have an applied part on your medical device, if you need to do applied part to applied part high pot. That's something very discreet that a lot of people, if you have an applied part, should be doing, but not many know about it. Again, if you would like a copy of this presentation or any previous presentations, feel free to contact Allison at allison.oba@arisafety.com, or you can check out our website at arsafety.com. Also, feel free to follow us on LinkedIn, Twitter, and YouTube. Especially if you follow our feed on LinkedIn, we're constantly giving industry relevant news and just interesting articles that we find that could affect what you're doing. Other than that, if there's no questions.
Hi, Anthony. No questions at this time.
Yeah, Anthony, no questions, but I think
So
people will be.
It's like there's no questions, so we can end our webinar there. We appreciate everyone for attending, and we look forward to everyone coming back next 2 weeks for line leakage testing 101. So thank you.